Okay, so in this problem, we have a horizontal platform in the shape of a disc, this guy right here. It's rotating freely on a horizontal plane about a frictionless vertical axle, so this middle axle, no friction. The platform has a mass, so we're given the mass of the platform, and a radius. And then we have a student on the platform, so the mass of the student is 60 kilograms, and they walk slowly away from the rim towards the center. So if the angular speed of the system is 20 radians per second when the student is at the rim, what is the angular speed when he reaches a final radius from the center? So we know that the initial angular speed, so Wi is equal to 2.0 radians per second, right? So that's what he was when he was at the rim. Okay, so let's see. So we're trying to find the final angular speed, right? We want to know what it is, and we know that the radius changes. So the initial radius on the outside, right, is equal to 2 meters. And then this radius on the inside is going to be equal to 0.50 meters, right? We have just the mass of the two objects, right? So then the mass of the disk equals 100 kilograms. And then we have the mass of the student equals 60 kilograms. Okay, so what's going on here? Well, he's moving, right? This is very similar to our conservation of momentum problems here. So he's moving. We're bringing the mass in towards the center. Okay. In this case, and our angular momentum is going to be conserved. Okay. So we know that our initial angular momentum is going to be equal to our final angular momentum, right? But the kinetic energy for the system is going to change, right? Because by going from here to here, he's basically adding a change in kinetic energy to the system. His motion is changing. He's moving linearly. So his well, I guess it doesn't really matter that he's moving linearly, but basically he's moving in, and so the kinetic energy of the system is going to change, and he's going to be spinning faster because he's doing work, putting work into the system. So let's start with the first part, finding the angular speed, and then we have a follow-up question kind of about this problem. Okay, so all right, what is our initial angular momentum? So let's find them each separately. So we're going to set Li equal to Lf, and then we're going to try to find Wf here, okay? All right, first off, what is our initial, so our equation here, Li is equal to the initial mass moment of inertia, right, times the initial angular velocity. So we have Wi. What is the initial mass moment of inertia? Well, we have two objects, right? We have a disk, which is 1/2 mr squared. So from our lookup table, so the disk, and then the radial distance just from the edge of the disk, right, to the center. So how large the disk is. But then we also have this person, right? This person is going to be modeled as a point mass. So I for a point mass is equal to, is just equal to mr squared. But it depends on what his radius is. So we have the radius of the disk, and then we have a person, and his radius is m large r squared when he's right outside on the edge, right? I think in the picture he's kind of shown in the in-between. So at the very beginning, we know he's on the rim. So he starts on the rim, walks slowly from the rim. Okay. All right, so that's the initial. So we know Li is going to be equal to 1/2 mr squared plus mr squared. So finding our mass moment of inertia by the mass moment of inertia of the object plus a point mass, and then the distance that point mass is away from the center of mass for the larger object. So you have to look at the shared, or the distance that object is away from the rotation point, sorry. So this is the rotation point in the middle there. Okay, and then we have Wi, which we are given. Okay, so what about Lf, right? So we're looking for Lf over here. We found our Li expression over there. Okay, what about the final angular momentum? Okay, so we're looking for, so we're going to have If, Wf, right, for the final. We are trying to find Wf, so let's ask ourselves what If would be. Okay, the initial or the final mass moment of inertia. Well, he's going to be moving, so that's going to change for us, right? The geometry for the mass moment of inertia is going to change, and so we need to calculate a new one. So his final mass moment of inertia is going to be equal, so the mass moment of inertia for the disk would be the same, mr squared, okay? And then because he's moving, he's going to be at a different radius away, right? We're going to have that change in the radius. So we're going to have plus m times this little r squared, right? Because he went from this larger radius, right, initially, to this smaller radius at the end, right? So his radius changed as he moved in towards the center. So that's going to change this mass moment of inertia, right? Okay. So the tricky part for angular momentum is a lot of these mass moment of inertia values might change in your problem. So we have to kind of be aware of what's going on, okay, and how that affects our overall results. Okay, so now let me plug stuff in here, right? So I have LF is equal to LI. LF, I have 1/2 mr squared plus m little r squared, right? And then I have WF, and that's equal to 1/2 mr squared plus big R squared, right? Times WI. Okay, so let's see what values I have and what I can plug in here. Move this to, okay. So I have my large R value. Well, actually, let me just algebraically solve for WF first, and then I can plug everything in. So I know that WF would be equal to 1/2 mr squared plus m big R squared, right, times WI divided by 1/2 mr squared plus m little r squared. Okay, so that's my expression. And this is what I was trying to find. So this is technically the solution to my problem if I was doing this symbolically. Okay. In this case, we were given values. So when you're asked to solve these symbolic problems and you're not given values, you're just solving in terms of the variables that you're going to treat as values because the problem gave them to you to use. But in this case, we were given actual numbers. We can plug some things in here. So we were given, we have big R. We know what that one is. We were given little r. We know what little m is. We know that what big M is. And we can plug those in just from up here, right? So we have big R is equal to 2.0 meters. Little r was equal to 0.50 meters. Little m was equal to 60 kilograms, and that was the mass of the student. And then big M of the disc was equal to 100 kilograms. So in this case, we just plug them all in. And then our WI was equal to 20 or 2.0 radians per second. Okay, so at this point, if you just plug in the values that you were given here, we get a WF that is equal to 4.1 radians per second. Okay, so that is the final value, right? Oh, I don't know why that turned into an arrow, sorry. That is the final value of the angular acceleration here. Okay, so we knew that momentum was conserved. We found both terms, right? We found the initial momentum terms and the final momentum terms for angular momentum. We plug them in on either side, and then we just solve for our WF, okay? So a change in the radius meant a change in the mass moment of inertia for this problem, right? Because as you moved in, it changed the mass moment of inertia, but because the angular momentum was conserved, we get set the initial equal to the final and then solve. Okay, one follow-up question. So what if we measure kinetic energy before and after this guy moves? So we'll say that he has like this initial kinetic energy, right, on the rim, KE initial on the rim out here, and then he's going to move some distance in, and he's going to have this KE final, right, where he's coming in, and we're going to call this like little r. We don't know what, well, little r was what, 0.50. So that's maybe not drawn to scale, but we start here, right, and then we end up here. Okay, so there's some change in r, right? Okay, so what's the kinetic energy? What happens there? Let's go ahead and model that and kind of answer that question as well. So we know that our kinetic energy for both states of the system is going to be rotational here. Okay, let me move my work over so that maybe I can do this kind of on the same page in a way that's sort of visible. I'll actually take this down a little bit so I can kind of write it up next to And then we know that this is just I have a point mass. Okay, so all right, what's going on here? Okay, so my kinetic energy initial when I'm on the rim. Okay, it's going to be rotational, right? He's just moving, he's rotating. So I'm going to look at that final point before he moves, and then, or the initial point before he moves, and then the final point when he's done moving, and then we're going to see what happens. So the initial point before he moves is 1/2 II Wi squared, right? We're given this initial, right? Okay. Then my final kinetic energy, right? KEF is equal to 1/2 IF W WF squared. Okay. So we have all these terms, right? We have so we have this initial angular momentum initial mass moment of inertia, and we have this final mass moment of inertia. We have this WI, and we just solved for our WF, right? We found that WF. We have that as well. So if we just plug in the values to both of these, basically, we're going to get some numbers here. So the initial kinetic energy for the system was going to be 880 joules. And then the final kinetic energy for the system is 1.81 times 10 to the 3 joules. Wow. Okay, so the final kinetic energy is higher, right? KEF is greater than KEI. Okay. Weird results, right? Why do we have more kinetic energy? What's happening here, right? Well, we actually do some work in the system. This guy does work by moving in, okay? So he is essentially, because he's putting work into the system, we're increasing that final kinetic energy, okay? So even though the momentum itself is conserved, we have more rotational kinetic energy, right? He starts to spin faster as he goes towards the middle. That's why we see that phenomenon when people, when kind of like you're spinning and you pull your arms in and you start spinning faster for like a figure skater, or you're in like an office chair and you're spinning and you pull all your arms in and you start to rotate faster. It's the same idea. Okay. So this is kind of similar to the one that we saw last week where we just had this little like block on a table and we were pulling it through a loop, but I just kind of wanted to hit a similar problem. This is very close to, I think, what you have on one of your homeworks as well. Okay, so let's move on to the next one. I think we're doing, and then there's one more example. The next problem down here, we're going to deal with with angular momentum that's conserved during collisions.